Welcome back to The Explainer. Today we're diving into Episode 4, Mathematics, Part 1, focusing on Pythagorean triples and database topology. And man, we are embarking on a wild journey today. We're going to take a fundamental concept from ancient Greek geometry and follow it all the way down the rabbit hole to modern serverless database infrastructures. I know, it sounds like pure science fiction, but as you'll see, it is absolutely rooted in elegant, unbreakable mathematics. Okay, let's just fly through our roadmap for today. We're covering 5 main beats. Number 1, the root node of 3, 4, 5. 2, the spatial geometry of triples. 3, the scale symmetry base. 4, stable fractal coordinates. And finally, mathematical database topology. All right, kicking things off with Section 1, the root node 3, 4, 5. To truly grasp where we're going with all of this, we've got to ground ourselves in something universally understood before we zoom out to the infinite. So 3, 4, 5. It's that iconic, punchy, primitive Pythagorean triple, the classic right triangle where 3 squared plus 4 squared equals 5 squared. But, in number theory, this isn't just a basic shape. It's actually the fundamental root node of a highly structured, non-halting ternary tree, specifically Berggren's tree. Literally, every single primitive Pythagorean triple in existence descends directly from this one single node, branching out infinitely into 3 children at every single step. Moving right along to Section 2, the spatial geometry of triples. Let's look at the macro level and see how this builds into an incredible 3-dimensional geometric structure. So when we embed these descendant triples as coordinates in a 3D space, R3, they don't just scatter randomly, no way. They reveal this deeply sophisticated, rigid geometric order. Check out this plane equation. 2x plus 2y minus 3z plus 1 equals 0. If you mathematically scan this entire infinite plane, guess what? It contains exactly one primitive Pythagorean triple. Just one. And it's our root node, 3, 4, 5. This really highlights how the branching of these triangles represents a highly specific, mathematically constrained spatial asymmetry. Now, as this ternary tree grows, it strictly obeys a bizarre but honestly beautiful geometric conservation law. Every node passes down physical properties to its 3 children perfectly. Specifically, the excircle radii of a parent triangle become the exact in radii for its 3 descendant triangles. So for example, our root node of 3, 4, 5 has excircle radii of 2, 3, and 6. Look at its 3 immediate descendants in the tree, and their inner circle radii are exactly 2, 3, and 6. This precise preservation means the tree is growing under strict, unbreakable geometric conservation laws. And this brilliantly illustrates how the tree maps to a strictly self-similar fractal, much like the Mandelbrot set. In fractal geometry, a self-similar object contains smaller, complete copies of itself. So by infinitely generating triangles from that original root node, we're not just looking at static math. We are looking at a non-halting recursive autonomon. It's a structure that can scale infinitely without ever losing its mathematical integrity or shape. All right, Section 3, the scale symmetry base. To really understand how this geometry bridges over into computer science, we have to look at the exact math that makes this infinite scaling possible. The absolutely crucial point here is this seemingly simple formula. X equals C minus B, all divided by A. So, in a right triangle, A and B are your orthogonal sides, and C is the diagonal hypotenuse. By algebraically removing the orthogonal measures using this equation, we effectively strip away the finite dimensions. And what's left over? An irrational, non-halting ratio. This formula acts like a secret decoder ring, unlocking the core recursive value of the triangle. We call this extracted ratio the scale symmetry base. By locking in this ratio and using it as an exponent recursion, we generate an infinite stack index. So why does this matter to us? Because it gives us a mathematical engine capable of generating unique, scale-symmetric geometric patterns indefinitely. Every single coordinate it spits out is mathematically guaranteed to be totally unique and perfectly ordered. Which naturally brings us to Section 4, stable fractal coordinates. Let's actually apply these mind-bending math concepts to software and database engineering. Consider this profound idea. The program and the data are structurally isomorphic. This right here is the foundational philosophy behind a hierarchical script database, or HSDB. You see, in traditional software, developers build these distinct layers, the database schema to hold the nouns, and the application logic to act as the verbs. And that separation creates massive friction and overhead. But in an HSDB that utilizes our scale symmetry math, the application's code execution path and the database's retrieval path become the exact same thing. Code as a verb and data as a noun become one isomorphic entity. It completely bypasses traditional object relational mapping overhead. It's a real game changer. But here's the catch. If we're dynamically generating infinite fractal coordinates for our data, how do we guarantee we won't lose anything? Well, the answer is an algorithm called Pythagorean descent. Because of that mathematical stability we just talked about, we can start at literally any primitive triple node deep in the infinite tree. By applying unimodular inverse matrices, we can just traverse backward. And since the math is absolute, this descent must be finite. It is guaranteed to terminate uniquely right back exactly where we started, at the root node of 3, 4, 5. The math literally ensures you can never lose your data. Finally, let's wrap up with Section 5, Mathematical Database Topology. We're going to examine the profound architectural shift this whole concept demands from modern software developers. Here is the absolute aha moment of today's explainer. Traditional databases like CouchDB rely on mechanical consistency, right? Their crash resilience is rooted in the physical reality of a hard drive head sequentially appending data to a disk, promising never to overwrite old bits. It's physical, and honestly, it's clunky. HSDBs shift this entirely over to mathematical consistency. State is modeled as scale-symmetric iterations along an infinite geometric number line. If a state is lost, it doesn't matter, because it can be mathematically derived again instantly. We're trading the heavy physical limitations of hardware for the elegant, weightless guarantee of consistency rooted purely in continuous, unbreakable fractal coordinates. As we wrap up today's explainer, I want to leave you with a provocative question to chew on. What other physical engineering problems can be completely bypassed by treating code and data as structurally isomorphic mathematical entities? Think about it. If we can eliminate the heavy overhead of database storage using the geometry of a simple 3, 4, 5 triangle, what other limitations in computer science are just waiting to be mathematically erased? Thanks for joining me on this deep dive into the intersection of ancient mathematics and future technology.